Let's look at an example of a linear model. We will analyze the returns by the Google stock using what is called the CAP and modeling econometrics. So we will take returns of the Google stock, that's our Y variable here, and we're going to regress it into the returns of S&P 500, which is our X variable here, and we will estimate the slope, beta, and the intercept, alpha, or beta 0 as we called it before. So as I mentioned before, alpha and beta are used in finance instead of beta 0 and beta 1. And we would like to know the estimates of those values, so we're going to call them alpha hat and beta hat. And then we will try to do some hypothesis testing, because you remember that beta, the slope, follows a normal distribution. And actually so does alpha. Alpha also follows normal distribution. And once we know that something follows a normal distribution, we can calculate confidence intervals about those values, or we can do some hypothesis testing. And one of the hypothesis tests, for example, is Google related to the market? So let's think how this hypothesis test can be written in terms of the coefficients beta and alpha. So coefficient beta is the coefficient that tells us how much of a change in Google we see when S&P 500 changes. So if they are related to each other, then we should expect beta to be a non-zero value, right? So hypothesis that corresponds to this question, so the hypothesis is beta equals to 0. So in our hypothesis, our status quo is that there is no relationship, and then we have to collect enough of data to convince us otherwise. So the alternative hypothesis will be beta not equal to 0, meaning that Google is related to market. And the next question is whether Google is better than the market. It shouldn't be Nvidia here. It should be S&P 500. Okay, so the question is whether Google is better than S&P 500, and the way we're gonna test this hypothesis is by looking at this alpha. So better means that when S&P 500 on a specific year returns 0, so it gives you no return, we want Google return to be positive. Okay. And you remember that the way we're going to measure the return of the Google on the day when S&P 500 doesn't return anything is just this value alpha, right? If S&P returns 0, then Google return is going to be alpha. So another way to write down this hypothesis is alpha equals to 0. That's our null hypothesis. So we assume the status quo is that Google does not outperform the market. So if market returns 0, then Google returns 0 as well. So the alternative hypothesis is alpha is not equal to 0. Or we can do one-sided test here, right? Instead of saying alpha equals to 0, we can say alpha is less or equal than 0, so Google is actually worse than the market, and the alternative hypothesis is Google better than the market. All right, so let's look at the data set. You see the scatter plot. This is data for Google return versus S&P 500 returns, and you can see that linear model is relatively good assumption here. We have a few outliers here. We have an outlier here when S&P 500 barely returned anything and Google had a huge drop. And we also have an outlier here. Also S&P 500 return was close to 0, but Google return was close to 4%. Usually those outliers corresponds to the earnings dates. So company reports the financial results of a quarter, and sometimes there's nothing happens on the market, so market stays flat, but specific company reporting good or bad result might move the value of the stock for the specific company significantly up or down. Okay, so let's feed the model. We're gonna use a lamp function from R, and we will feed the returns of Google, and we're gonna regress it into S&P 500 returns. And here are the values that we get. We get the intercept, so our alpha is positive, okay. But then the question is whether this positive alpha truly positive or not, and we're gonna look at the uh, t-value and p-value. And p-value actually is 0.164. So if we try to test at the 95 significance level, then we basically, if we try to test the hypothesis, null hypothesis alpha equals to 0, then at the 95% significance level, we cannot reject this hypothesis. Cannot reject. So basically, our model tells us that on a day when S&P 500 returns 0, Google will also return 0. So Google is not significantly better than the S&P 500. And let's look at the value of the beta coefficient. So beta estimated, so the estimated value of the beta head that came out of the model is 0.9232, and the p-value is 10 to the negative 16, and you remember this p-value that is printed by R is associated with the null hypothesis that beta hat actually equals to 0. So for the beta hat null hypothesis, whether it equals to 0 or not, we have to reject it, and accept alternative hypothesis that beta, the true value of the beta, is actually not equal to 0. Okay, so that's a true value of beta here. Beta. All right. So we were able to test the hypothesis and answer whether Google actually outperforms or doesn't outperform the market. And now, if we try to understand how much will Google move if market goes up by 10%, well, the beta coefficient tells us exactly that, right? So if market goes up by 1%, we should expect Google to go by 0.9232%. And the T ratios, the p-values, shows us that yes, Google is related to the market, and no, Google does not outperform the market. So the alpha coefficient cannot be, we cannot say that it is different from 0 from statistical point of view on the 95% assumption level. All right, let's talk about outliers. So we talked about this concept very briefly before. So if you have a data set and most of the data is around this trend line, and then you have certain observation that is far away from this line, okay, and so far, so the distance is large, and we call this observation an outlier. So this is an outlier. And there is no strict rule what should be called outlier. We shouldn't be called outlier, but rule of thumb tells us if on standardized scale the residual is greater or equal than 3, then we call it an extreme outlier. And you remember the standardized residuals are just residuals measured on the standard deviation scale. So means so greater or equal than 3, meaning that this specific point is more than 3 standard deviations away from this line. So you remember you take an average and you calculate how many standard deviations away. So that's a standardized residual. So that's just a rule of thumb. And again, we expect that 95% of the residual is going to be between -2 and 2, or to be more specific, 1 minus 196 and plus 196. But 2 and 2 is roughly a good approximation to this number. Okay, so another concept is influential points. Influential points are the points that affect the regression line, meaning that if you remove an influential point from the dataset, your regression line will change significantly. So usually regression points will be the points that are, so there are two types of influential points. An outlier, usually an influential point, but not always. So let's say you have a data set like this, okay, and you fit a line to it. And let's say you have this point here, okay. So whether this point is part of the data set or not will not affect the line significantly. So if I remove this point, if I'm to remove this point, the line will stay pretty much the same. So meaning that this point is not an influential point, although it is an outlier. So that's example outlier, but not influential. So outlier is not always influential, okay? There are two characteristics of influential points. So usually it's an outlier, but it also is far away from the middle of the, so if this is x bar, y bar, so that's the middle of x and y, and an influential point should be far away from this point. So if you have a data set, let's do the same data set, and you have this line that fits in the data set. So this point here will be an influential point, because if you remove it, so let's look at the plot without this point, and then let's look at the how the fit will look. So it's going to be the same data set, okay, but we're going to just add this influential point here. So the line will be something like this, okay. So then we say that this point is influential. And it's also an outlier. Usually all of the influential points will be outliers, but not all the outliers will be influential points. In order for a point to be influential, again, it needs to be far away from the as this x bar, y bar location. Okay, and in order for us to measure whether something is influential or not, we're going to use what is called Cook's distance. Cook's distance just measures the effect of this point on the regression line. So large Cook's distance means that the regression line will change a lot if this point is added or removed from this data set, and small Cook's distance means that the regression line will not change. So for this point, it will have, so it's not influential point means Cook's d or Cook's t distance is small. So the regression line is not affected by this point. And for this point, the Cook's d distance is large. So we use this Cook's d distance to measure whether the point is outlier or not. And the nice thing about linear model that those Cook's d distances come as a byproduct of the estimation process. They come as a byproduct of the estimation process or algorithm. So you basically don't need to do any extra calculations, and actually LM function in R will do it. Will do it for you. Okay. So you basically have to call this Cook's distance on the model, and everything that is required for this Cook's distance function will be already in this model object that is output of the LM function, and you can calculate those Cook's distances. Yeah, so essentially that's what Cook's distance is trying to measure, whether coefficient beta 1, when you estimate it with observation I being removed, is different from the beta 1 when it's estimated on the full data set. So what happens to the slope beta 1 if we remove a specific observation I? and this difference between two slopes will tell us whether this point I is influential point or not. Okay, and also there is no real hard rule to say what's influential point, what's not, and we usually will use some type of rule of thumb. We'll say whenever Cook's distance is greater than 1, we're gonna call this point an influential point. And we're going to look at an example, but whenever you see influential points, you always have to think whether this point should belong to the data set or not, because you remember influential point changes your estimate, and it's up to a modeler to decide whether to keep this point as part of the training data set or not to keep it. And often I delete point with the largest Cook distance just to check if it doesn't affect the conclusions. So it's one of the modeling considerations what to do with those influential points. We'll look at an example. So here's a summary of how the linear model is to be built. So we start by plotting the data. So we'll look at the scatter plot using the plot command and the box plot. So that's called exploratory data analysis. Exploratory data analysis, or EDA. So we just visually looking at the data. Then we build the regression model. We just use LM, Y regressed on the X. And then we do the diagnostics of the model, because you remember we want to test whether the 4 assumptions of the linear model are satisfied or not. And we're gonna look at what is called a QQ plot. I will explain a little bit later what it means. Then we see whether there are influential points in the model, whether there are outliers in the model. And then if we need to do interpretation of the model, then we can look at the coefficients estimated by the LM, and then we can do the predictions. So there's two. So once we build the model, so that's kind of step 3 is verification process. So step 3 tells us, hey, you got a good model. So it's kind of a certificate. As a result of step 3, you want to get a certificate that it's a relatively good model that can be used for interpretation. And you also, before you start predicting, you want to measure your, remember, S squared, small, then model is good for prediction. So we want to test 2 things: whether the linearity assumption is satisfied, the assumption of a linear model, meaning that coefficients beta will be correctly estimated, because if one of the assumptions is violated, then coefficient beta is not correctly estimated, and then interpretation of the model can suffer. So step 3 provides the certificate for the step 4. So that's like, you can think of it as a certificate that these models can be used for interpretation. And S squared provides the certificate for the prediction. So that's also a certificate for the prediction. So before you start using the model for the prediction, you want to make sure that the residuals are small, because if the residuals, even for the data set that's used for training, is large, then the model cannot be trusted. And again, but if you only care about the prediction, you don't care about the interpretation of the model, then you should only care about the S squared. And in this case, a model is only as good as its prediction. So for this case, when prediction is the only thing we care about, we might actually as well ignore the linearity assumption, and even if we don't get the certificate from the step 3, we say, okay, maybe there's some violation of the linearity assumptions, but we still can use model for the prediction as long as those S squared are small.